In lesson 5.6, you learned how to find signed areas using definite integrals. Not all such areas can be found this way. Some functions cannot be integrated. They are said to be non-integrable, and sometimes you are given data or a graph but not an actual function. It is still possible to approximate areas. In this lesson, you will approximate areas by adding areas of rectangles. This sum is called a Riemann sum. Example 1. Approximate the integral of f of x from 0 to 10 by adding the areas of the 5 rectangles shown. This can be shown as the following. But notice that 2 is the base of each of our rectangles, so I could write it like this. In fact, that is how AP wants to see a Riemann sum. So what are the requirements for AP in order to get full credit for a Riemann sum? You must write that standardized width being multiplied by the sum of the heights. It's a Riemann sum. What do they want to see in order to give you full credit? They want to see an actual sum. If your width is not standardized, then you wouldn't need to write it. You would write it as the sum of areas. This is called a midpoint Riemann sum. The height of each rectangle is determined by the y value of that middle x. So this height was f of 1, this height was f of 3, this height was f of 5, and so on. The heights of the rectangles are determined from the midpoints of intervals. Be sure to use f of x values, not x values, for your heights. In many cases, the rectangles used to approximate areas are of equal width. In such cases, you can use a formula to find the Riemann sum used to approximate the area. Dun, 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 dun. Note that the number of heights will equal the number of rectangles. The width can be found by taking b minus a and dividing by n, the number of rectangles. For number 2, let's approximate the integral from 0 to 10 of f of x by using 5 rectangles of equal width and an upper circumscribed Riemann sum. For an upper circumscribed Riemann sum, the heights of the rectangles are determined by the upper or the largest f of x value in each interval. 5 rectangles of equal width. Each of our rectangles should have a width of 2, but their heights are determined by the largest f of x value. So the largest f of x value between 0 and 2 is f of 2. That will be the height of this first rectangle. The highest f of x value between 2 and 3 is f of 3. The largest y value for this one is on the left side, the left corner of this rectangle. The largest y value is on the left and right side of this interval. The largest y value here is the right hand rectangle. Writing our Riemann sum as a sum would be width times the sum of the heights, which gives us 40. Show that sum and show the result. We are integrating the same function with the same number of rectangles, but this time we're using a lower inscribed Riemann sum. The lowest y value of each interval will be chosen as the height of the rectangle for that interval. This lowest value between 0 and 2 is 0, so there's no rectangle between 0 and 2. The lowest value between 2 and 4 is at f of 2 or f of 4. The lowest value between 4 and 6 is at f of 6. Between 6 and 8 is at f of 7, and between 8 and 10 is at f of 8. Show that sum, and our result is 18. For number 4, same graph, same integral, different number of rectangles, and we're using a right hand Riemann sum. If our number of rectangles is 10, this time our width is 1. Right hand means the height of the rectangle is f of the furthest right value of x for each interval. So the right hand y value is the height of our rectangle. Right hand, height of the rectangle. Notice that when f is increasing, a right-hand Riemann sum is an overestimation of the area under the curve. But when f is decreasing, a right-hand Riemann sum is an underestimation. Calculate the area. which is 31. All right, this time we have a different graph, and we're going to use midpoint Riemann sum like we did in the very beginning. 3 equals subdivisions, so n is equal to 3, which makes our width 2. The heights of these rectangles will be determined by the y value of the middle x value in each rectangle interval. The middle number between 0 and 2 is 1, so f of 1 will be the height that we use. Halfway between 2 and 4 is 3, so f of 3 will be the y value we use here. F of 5 will be the y value for this final rectangle. And that is because I'm calling f of x this function in the integrand. Our area is width times the sum of the heights. How do I get those exact values if it's between 3 and 4? Oh wait, this time they gave me an actual function, so I can plug those in. And if we were allowed to use a calculator, this decimal approximation is 27.183.
It is possible that f of x is not always greater than or equal to 0, and or that your subdivisions do not produce intervals of equal width. You can still approximate values for definite integrals by using a Riemann sum. Approximate the integral from -10 to 5 of 2 to the x minus 8 dx by using 5 right-hand rectangles whose widths are determined by the interval separating the following x values.
The width for our first rectangle is 6. The height is the right side y value, so that would be h of -4. Next, our width is 4. For a right-hand rectangle, we use the y value at 0. The next rectangle has a width of 2, and its height would be h of 2. The next width is from 2 to 3, so 1, and our y value, our height, would be h of 3. And if you can see, h of 3 is 0. Our final rectangle has a width of 2, and the height is the y value taken at 5. We can find each of these h values by plugging in x into our function h of x, 2 to the x minus 8. Fill in your y values into your Riemann sum, find the answer without a calculator, and then give a decimal approximation using a calculator. Here's our decimal approximation, and remember you would have to show either the sum in the first step or the sum in the second step to get full credit for a Riemann sum on an AP exam.